Sairam and welcome to this session on dot products. Let us begin this session with a prayer. Om Sai Ishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarvah Prachodayat. Om Shanti Shanti Shanti. Remember that in the previous session we looked at an interesting concept called finding the length of the shadow of one vector on another. It's like projecting a vector onto another and finding the length of the shadow. Okay. Now that led to an operation between two vectors which we defined as the dot product. And how did we define that? We said that A dot B is going to be defined as the product of their magnitudes times cos theta, where theta is the angle between the two vectors A and B, right? So you could also call that theta as the angle between A and the unit vector in the direction of B, but it doesn't matter. We know that the angle is going to be the same. Okay. Now, just from this, we are going to look at some very interesting properties, and it will also give us a lot of insights about dot product, and that will make us appreciate why this operation called dot product itself is being used. Okay. Now let's ask, what is the, if you remember, this is the idea that prompted us to bring up dot product. We said, what is the length of the shadow of A on B, right? And this we came up and we said that length of the shadow will be magnitude of A times cos theta, but remember the theta is the angle between A and B. Now similarly, if I ask, what is going to happen to the length of the shadow of B on A, right? So how will that be? Right, so if I call that as let's say the shadow of B, just to denote it, let's say that we call the S subscript A and S subscript B, this would be obviously the magnitude of B times cos theta. Now remember that the theta is the same because the angle between A and B or B and A is going to be the same, right? And therefore this part, the shadow and the length of the shadow of B on A is going to be magnitude B times cos theta. Okay. Now remember, the length of the shadows need not be the same, but using this we can actually look at this product, right? So let me attempt this here below. So we got A dot B is equal to magnitude of A times magnitude of B times cos theta. Okay, so I can now write this as, so how did we come up with this? First we said this is going to be, initially we did this with the unit vector, brought this magnitude of B here, initially taking the the shadow length to be of A to be magnitude of A times cos theta. Whereas here, now what I am going to do is, I am going to say that this is magnitude of A times magnitude of B cos theta, right? So if I write it like this, what does it mean? It says it's basically the length of the shadow of B, right? And you are multiplying this with magnitude of A. And what does that say? That says that this is the dot product of, this is the dot product of B and A, is it not? Right. So remember, what is A dot B? A dot B is the length of the shadow of A times the magnitude of B, right? We had A dot U and brought this, we said U is B by magnitude of B and brought this B here. Therefore, this became A B cos theta. Now, if I separate this B cos theta, what does this say? This says that this is the length of the shadow of B. Oh, okay. So if this is the length of the shadow of B, this times another magnitude of A, what does that represent? That represents B dot A, because we are now looking at the shadow of B. Therefore, look at the product, look at the operation dot product. What can we conclude? That we can conclude that this is a symmetric operation, right? Even from its simple definition, we can make out it's symmetric, but this will make it more conceptually clear, and that's why I went through this. But idea is simple, because this is just a real number product, and we can simply change this, because normal real multiplication is any day symmetric. So this can be written as other way as well, and therefore we can make this as B dot A, right? So I hope that we have understood that dot product is symmetric. Okay, let me talk about another interesting property. So let's look at this. So here I'm writing theta 1, right? Theta 1 is the angle between A and the x direction, positive x direction, whereas theta 2 is the angle between B and x. Okay, now let's say that we want to talk about the dot product of A and B. Okay, so that means that we have to write down here saying A dot B is equal to magnitude of A times magnitude of B cos, what should I say? Should I say theta 1 or theta 2? Right? It can't be theta 1 or theta 2 because this angle says that we must take the cosine of the angle between A and B. And what is the angle between A and B, right? So we will have to measure this angle here, the theta 3, and can I say that the theta 3 is nothing but theta 2 minus theta 1, right? So instead of writing theta 3, I am going to say theta 2 minus theta 1, right? And let's expand on this formula, right? So this is going to be magnitude of A times magnitude of B. Cosine of A minus B is cos A cos B plus sin A sin B. So let me expand this out and say that this is going to be cos theta 2 cos theta 1 plus sin theta 2 sin theta 1. So let me expand this now. So this can be now, can I write like this? So I am going to say this is cos theta 1. I am just arranging the product in a way where it will start making better sense for us. So I have written this as magnitude of A times cos theta 1, magnitude of B times cos theta 2 plus, similarly this will be magnitude of A times sin theta 1 and magnitude of B times sin theta 2. Okay, now let's look at this and ask ourselves, what does this represent in this diagram, right? So I am now interested in what is going to be A cos theta 1 or magnitude of A times cos theta 1, right? So let's look at this. I have the A vector. This is the magnitude of A, that's the length of A. Cos theta 1 must be the adjacent by hypotenuse. So let me drop a perpendicular here, right? So this is the part that we are looking at, right? It's essentially the shadow, length of the shadow of A, right? So this part is what we are looking at, which means if I represent this vector as an x component comma a y component, right? We used to use numbers, but I'm just trying to use now notations to make it more general, and therefore magnitude of A times cos theta 1 is going to be this Ax, right? This much, right? The shadow, right? So this part is going to be Ax. So this I am going to write this as Ax, which is the x component of A. Okay. Now let's look at B cos theta 2, right? So it's a similar idea, right? So if you drop a perpendicular here, and now we are looking at theta 2, right? Theta 2 means again now this is the shadow part, right? So if again let's give it some coordinates here for B, let's call it Bx and By. What would happen now? We are looking at cos theta 2. Cos theta 2 is the shadow of B by the hypotenuse. We are multiplying that by the hypotenuse, that is the length of B. Therefore you're going to get the length of this part here, and therefore that part is actually Bx, is it not, right? So this part is going to be Bx. Okay, plus. Now look at this must be simple now. So magnitude of A times sin theta 1. Okay, so here it is, magnitude of A times sin theta 1. That's going to be this part, which is the y component of A, and similarly B sin theta 2 is going to be the y component of B, right? So therefore this is going to become AY times BY. Well, look at the interesting formula that we have come up with. We said that A dot B is actually their product of their magnitudes times cosine of the angle between them, but now it says you don't have to take all that square roots and squares and add them, etc. It's going to become a little simple for us. It is only Ax product of their x components and summation with the product of their y components, which are just real multiplications and added together, this computation is extremely fast compared to this computation, right? So it's a very, very useful formula for A dot B, and obviously, you know, we don't have to apply this in every dimension and then try. Rather, we can say if A and B are in n dimensions, so we can say that if they are in n column vectors or in n dimensions, what would happen? This can be now written as sigma I equal to 1 to n AI and BI, right? Where we are talking about A1, B1 and A2, B2, etc. These are the ith components in that specific dimension. Okay, a few more properties we'll look at. Now let's take a look at this diagram. Let's ask what is the length of the shadow of this vector, right? I'm looking at this y vector, let's say, right, on x. So assume that I have a light source here at this point, right, and let's say that we cast the shadow of the y vector on x. So it's something like asking how long is your shadow when you walk exactly at noon time, where sun is exactly above your head, right? And you know the answer, right? You know that you are not going to really cast a shadow. I mean, yes, physically, yes, there is some shadow, but the point is that if it is exactly upright, you will find the shadows on yourself. In fact, the length of the shadow can be measured to be 0, right? So that's what we are saying. Now let's see what happens to A dot B when we talk about such perpendicular vectors, right? So this is going to be times cos theta, and theta is the angle between A and B, right? And if it happens to be perpendicular, what is cos 90? That's going to be 0, right? So that's exactly what we're saying. So when we're talking about the length of the shadow, which is either you say A cos theta or you say B cos theta, whichever way you put it, you're finding that this product is going to become 0. So dot product becomes 0 for perpendicular vectors. Okay, and how is that useful? So if I have two vectors, I simply have to, you know, multiply their corresponding components, add them up, and if the summation becomes 0, I have something found, right? I have discovered something. I can find that these two vectors are perpendicular. So here is a very, very useful property of dot products. So let's take an example and try if that is really so, right? So let's try. So here's the simplest example I can talk about. So let's say that I have A vector is 1 0 and B vector is 0 1, right? We know what is A dot B, so you don't have to really calculate all this. Don't even bother about what's the angle, just look at this and we find that, you know, this is a 1 0 and that's a 0 1. Let's say 1 into 0 plus 0 into 1, that's going to be a 0. What does this imply? It implies that the angle between them has got to be 90 degrees, and therefore we get this idea that these two are perpendicular vectors, right? So if you go back to this formula and ask, is this the only place where this can go to 0? Why not the magnitudes, right? I mean, magnitudes of vectors are never 0, right? You can never have a 0 magnitude vector except for this single vector called 0 0. But then we know what we are taking non-zero vectors here, and therefore this is the one that's going to 0, and that means that they are perpendicular. Okay, one more interesting property, what happens to dot product of a vector with itself. So we could use this formula now. We are trying to use whichever suits us so that it becomes quite easy to find what is the answer. Okay, this is going to be magnitude of A times magnitude of A times cos of theta. And what is theta? Theta is the angle between A and A, and what is that? That is 0. So what is cos 0? That is 1, and therefore this is simply the magnitude squared, right? So when I want a dot product of the vector with itself, I get the magnitude squared. Okay, so how does that help us? If I want to find the length of a vector, I can bring it up from the dot product, right? If we have a fantastic processor that can calculate dot products quite quickly, then I think we don't need to find the length. We just say we find the dot product, and if you want to take the square root, we got it. Or if we compute this dot product and say that that's the square of the length, and then we have the answer with us, right? So we can see some quite useful properties of the dot product. Here is one example where we found that, using this formula we are able to find what's the angle between two vectors, and now we are saying that we are even able to figure out what is the magnitude of a given vector. Okay, those were some good real interesting properties. Now what we are going to do is we are going to take up this specific formula that we are looking at, right? The dot product is going to go to 0 when they are perpendicular, and we are going to try and prove this. Remember, we just looked at it geometrically. Is there a possibility that we can look at it algebraically and try to see if this really goes to 0, right? That's one thing we'll do. Before we move there, remember we talked about the 0 vector, right? Now what would be a dot product of any vector times the 0 vector, right? So how much will that be? Right, there's going to be the magnitude of A times magnitude of the 0 vector times cos of the angle, right? Let there be any angle, but we understand the magnitude of the 0 vector is going to be 0 and the dot product is going to go to 0. And if this fact is true, right, if this fact is true, then what means is that the 0 vector is perpendicular to any vector, right? So that's how we are going to define with respect to the 0 vector. And remember, 0 vector is one vector that you really can't draw, right? So it's just assumed to be that point in the origin, and we are, because of the dot product, what we define that the 0 vector is perpendicular to any other vector. Okay, now let's try and prove this algebraically. Okay, let's say that I have u and v vectors, and let's assume that they are perpendicular to each other, and let's also assume that their components for u is u1, u2, and components for v is v1 and v2. The first thought that we must strike is what is the vector that is drawn in yellow, right? So how will you think about it? I will request you to please think of what we studied with vector addition, vector subtraction, etc., and come up with something for this vector in relation to u and v, right? So you may pause the video here and then try to check what it is. Okay, so here is the idea. So let's say from origin I walk all the way till u, right? And after walking this much, after walking the yellow vector, effectively I have reached v, which means that u plus this x or the yellow vector is giving me the v vector, right? And therefore this must be the difference. So I'm going to write this as v minus u, right? I walk u and then I walk v minus u, I am going to reach v, because vector addition of u and v minus u is giving me v, right? Okay, now why did we come up with this? We are going to use the Pythagoras theorem here, and since this is the hypotenuse, we can square their magnitudes and add, and then we will be able to get the square of this vector's magnitude. So let me write that down. Because of the Pythagoras theorem, I can say that the magnitude of u square plus the magnitude of v square is going to be the magnitude of v minus u the whole square. Okay, now we can look at what is this vector v minus u, right? So let me write this down here. What would be v minus u? We know what is vector subtraction, is just component wise subtraction. Therefore this would be v1 minus u1 and v2 minus u2, and we know what is the magnitude of a given vector, right? So it is just their components squared, sum it up, and then we take the square root. But since there is a square already here, those square root and the square can be removed off, and what we are left here is going to be u1 square plus u2 square, right? Plus here we will have v1 square plus v2 square, right? The square is gone because of the square root. Okay, let's look at this and then try to understand what will be the magnitude of this vector. So the magnitude will be v1 minus u1 the whole square plus v2 minus u2 the whole square, but the square root of it, but there is a square here, so that's gone. Therefore effectively we are left with v1 minus u1 square plus v2 minus u2 square, right? So let me expand the right hand side part. So this we are going to get v1 square plus u1 square minus 2 u1 v1 plus v2 square plus u2 square minus 2 u2 v2, right? So we see here something that u1 square, many of these terms are getting cancelled, right? v2 square, v1 square, what you're left with is here. So what we're saying is u1 v1 plus u2 v2 is 0, right? This is what we are coming up with. And what does that mean? It means that u dot v is equal to 0. So we started with perpendicular vectors and we're showing that the dot product is 0. Okay, apart from perpendicularity, dot product is also, it doesn't show just perpendicularity. There is one more beautiful insight about dot products, and it can convey something about the two vectors. So let me take you to a diagram below. So what we are going to do now is we are going to look at u dot, we are going to keep this u vector with us, and we are going to talk about how is u dot v1 or u dot v2 etc. How are they going to look like, right? But before we do that, I want to make this important assumption clear to all of us. So with respect to the vector algebra that we are studying, we really need not measure about, we did talk about counterclockwise and clockwise etc. But we need not worry about all that. All that we need to look at is we are going to measure the angle between two vectors as the shorter angle between them, right? And therefore, and we are going to assume that's positive angles only, and for our purpose that is more than enough, right? So let me give an example. Let's say that we talk about u and v1, right? So there is one angle here and there is also a larger angle that forms on the other side. So the angle between these two vectors is considered to be the shorter angle, right? Therefore that will be theta. Similarly, if you talk about u and v5, there is one angle here and there is one more larger angle on the other side. We drop the larger angle, we only pick the shorter angle, right? So keep this in mind, and with this we will be able to draw a beautiful insight from dot products. Okay, let's first consider what is the length of the shadow of v1 on u, right? Okay, so what would we do? We would for u we will take rays of light that are perpendicular to it and cast the shadow of v1 here. So what would happen is, we would drop a perpendicular like that and get this, and then say that this is going to be the length of the shadow, and the dot product is going to be saying that magnitude of u times magnitude of v1 and cos theta, and remember the theta is this angle, right? So therefore let me just call it theta 1, because for u and v1 we're calling it theta 1. Okay, what's interesting here is that the shadow is look at the shadow direction, right? Look at the direction of v1's shadow. One thing is obvious, that it has to fall on u, and it is in line with u, right? It's pointing in the same direction as u, which means that both of them are landing into the same direction, and therefore the dot product is going to be positive. Okay, let's try and move to v2. Okay, now we can make out something very clearly here, that v2 is perpendicular to u, right? So theta 2 is actually 90 degree, and let's try to cast the shadow of v2 on u. We just looked at it and we found that the dot product is going to be 0, because there won't be any shadow cast. That length of the shadow is going to be 0. Okay, that is understood. Now let's talk about the v3 vector, which makes it much more interesting, right? Now look at the rays of light that are hitting perpendicular to u, and the light is shined on v3, right? It will cast a shadow, but remember now that the shadow falls on the other side of u. That means when we look at this shadow here, it's going to move in the opposite direction, or it is going to point in the opposite direction of u. And what does that tell us? It's going to tell us that if you pick up u and v3, their dot product is going to be negative. So let me just note this down somewhere. So what we're saying is u dot v1 vector is going to be greater than 0, positive. Now we also wrote this down. We know that this is perpendicular, and therefore this will be equal to 0. And now we are coming up with another fact. We're saying that since the shadow of v3 falls in the opposite direction of u, the dot product is going to come out to be negative. Sorry, so let me write this is less than 0. Okay, let's talk about v4. Okay, now we look at V4 and U, there are two angles, right? One is a smaller angle here, other is a larger angle on the other side. So let's not worry about the larger angle. We're only going to look at the smaller angle, and this time put the rays of light here, right? Perpendicular to U. Let the rays of light hit V4, and we are going to project this here. Similarly, you find that the shadow of V4 is coming out in the opposite direction of U, and what is that conveying to us? That's conveying that U dot V4 is going to be negative. Okay, let's talk about V5, right? So V5 we can clearly make out is perpendicular, and whichever direction it is doesn't matter. We are only measuring the shorter angle, and therefore we know that U dot V5 is going to be equal to 0. Okay, let's talk about another vector here. What if we have a V6 here? And I think that will make it complete. So I'm going to cast light from this side perpendicular to U, and that's going to we're going to cast the shadow here, and the shadow is in line with U, and therefore U dot V6, or the dot product of U and V6, is going to be positive, right? And what is the insight that this is bringing us? What it is bringing us is, when we look at the vector U and when we have a perpendicular, whatever vectors are on the plane where U lies, the dot product with all those vectors in U is turning out to be positive, right? You look at these two examples. Okay, similarly, when we look at the perpendicular and U, any vector that's going to lie on the other half of the perpendicular, or the other half plane, all these vectors, that is V3 and V4, it is becoming negative, right? You can clearly make out this, right? So that's the beautiful insight that dot product is giving us. Okay, now how did I even say that the dot product is becoming negative? What I know is only one thing. I can only say that if I talk about shadow of V3, I can only say that the shadow of V3 is in the opposite direction of U. Okay, and we can talk about the shadow of V4 being in the opposite direction of U. Now, how am I saying that U dot V3, how am I saying that the dot product is going to become less than 0, right? Okay, let's ask what is the shadow here, right? So let's say that this is actually V4 cos theta 4, or in this case, when we drop this here, the angle between this is, let's say, theta 3, right? So let's mark this as theta 3. The shadow is going to be V3 cos, will that be theta 3? No, it's not going to be theta 3, but it's going to be 180 minus theta 3, right? This specific angle, this angle here, right? So let me just write down what we are talking here. We're saying that length of V3's shadow is going to be the magnitude of V3 times cos 180 minus theta 3, right? Now, whatever value, let it come, but the point is, when we talk about this in terms of theta 3, what's going to happen now is cos of pi minus theta is going to become minus cos theta, and therefore this would effectively become minus cos theta 3, right? Remember that ultimately that length is going to be positive. So we are not saying the length is going to be negative. The length is going to be positive. It's going to become, so let me write this down. So this is going to become minus the magnitude of V3 times cos theta 3. You may really wonder, how is this length going to become positive when I have a negative sign here? The answer comes from here, right? If you look at the way cos, let me try and draw a graph of the cos angle. So it starts at 0 and it drops to 0 at pi by 2, and at pi it's going to reach minus 1, right? So this is pi, this one is pi by 2, and that is 0, right? We are trying to plot cos theta, right? This is 1 and here we have minus 1. Right, this is the plot of cos theta, you can see something interesting, that when we talk about theta 3, you see that theta 3 has gone beyond 90, right? When you see that cos beyond 90 is always going to be negative, right? And therefore, when you pick an angle here which is more than 90, this is cos of that is going to be negative. So in effect, this is going to be positive, right? Okay. Now look at the dot product, right? So let's try and look at the dot product. So we talk about u dot v3. What is it? The dot product is going to be the magnitude of u times the magnitude of v3. None of these terms are negative. Both will be all non-negative terms. And here we are going to talk about cos. What theta is this, right? What's the angle between u and v3? The angle is theta 3. And therefore, I have to write here cos of theta 3. And what did we just figure out? Any theta that's going to go beyond 90, we are going to see that cos is going to drop to negative, right? So it's going to drop below 0. And what does that tell us? That the dot product of u and v3 is going to be negative. And this is the way that I was able to derive and say that the dot product of vector v3 and u is going to be negative. Okay, now look at similarly, like look at v4. We find that there is a theta here, but the theta 4 here is more than 90, and that tells us that the cos of cos of the theta 4 is going to be negative, and therefore u dot v4 becomes negative. You can similarly work out for v1 and v6. I'm sure you are able to appreciate and understand. There is one fantastic insight that the dot product is giving us. Simply calculating the dot product and looking at its sign tells us where the vector v is located with respect to u. Is it on the same half plane as u, or is it on the other half plane away from u, right? Just looking at the dot product. And we have got an easy formula also for dot product, something of this order, where we can simply take the product of the components and add them, and we will be able to understand where this vector is lying. Let me ask you a question. Let's say I pick up u, which is a simple vector 1, 2. Let's say v is 2, 1. And if this question is asked, with respect to u, does v lie on the same half plane as u, or is it lying on the opposite half plane? How do we work that? How do we work that out? So we are simply going to calculate u dot v, and we'll say u dot v answer is going to be 1 into 2 plus 2 into 1, so that's going to be 4. That's greater than 0. And what does that tell us? That v is lying on the same half plane as u. Okay, let me pick up another example. Let's say another v. Let me write that down below. This time, let's say that I talk about a -2 and a 1 here, right? Okay, now with this v, let's calculate u dot v. What does that tell us? That's a -2 plus 2, that's 0, right? What does that tell us? So if I call this v1 and v2, I'm able to derive that u is perpendicular to v2. Okay, let me talk about another vector, let's say -3 and 1, right? And now let's talk about u dot v3. What is the answer? -3 times 1 plus 2, right? So that's going to be a -1, and it tells us that this is less than 0. What does that tell us? That v3 is lying on the other half plane away from u, right? It's on the other half plane. So this is very easy way to look at dot products, and we can calculate and find this insight where this vector is actually lying. So in other words, right, instead of talking about simple directions, let's talk about the actual theta. So if this is given, what can we talk about here? We can say that theta 1 has got to be less than 90 because it's lying on the same half plane. Here I know that theta 2 is going to be 90 because it's perpendicular. What can we talk about theta 3? Theta 3 is going to be greater than 90 degree, right? Maybe we will not get the exact angle from dot product, but we can get a rough idea of where it is lying. Okay, let me ask you another interesting question. What if we have u and v to be unit vectors, right? We know what are unit vectors. So here's the question. Can we talk about what would be u dot v when u and v are unit vectors? Okay, let's try and calculate. This is going to be the magnitude of u times the magnitude of v times cos theta, where theta is the angle between u and v, and anyway they are unit vectors. What would be the magnitude of u? It will be 1. What about v? Magnitude also is 1. Therefore, this is simply equal to cos theta. Okay. And remember, when we drew the cos graph, we saw that the cos theta can never go higher than 1, right? This is always, I can write this as saying, since this is equal to cos theta, the dot product of two unit vectors is always going to be less than equal to 1 and must be greater than or equal to minus 1, right? So you see another very important fact that's coming through, right? Okay, now let's say that we talk about two general vectors, right? Let's talk about two general vectors. Let's say I have A and B, two general vectors. So what would we talk about A dot B? We know that this is going to be modulus of A, magnitude of A times magnitude of B times cos theta. Theta is the angle between A and B. Now let us make them unit vectors. Okay, how do we make them unit vectors? We simply divide A by its magnitude and B by its magnitude, right? So I can even bring this on this side, and I can say that A by magnitude of A dot product with B by magnitude of B is going to be cos theta. It's a pretty simple observation. We just bring it here and then do, or even if we want, we can say that let me assume that A and B are two general vectors. Let me make it a unit vector, A by magnitude of A and B by magnitude of B, and just now we derived this fact saying that the dot product of two unit vectors has got to be cos theta. So here it is, I have dot product of two unit vectors, it's got to be cos theta. Now this is a very important fact. Let us now talk about what is the magnitude of this dot product. Oh, I'm sorry, we will talk about what is the modulus of this dot product. When I say modulus, right, so let's try and see what are the cos theta values. Cos theta values we just saw are from -1 to 1. And if we talk about what is the modulus of it, right, so please understand this carefully. This is not the magnitude, but this is just modulus. If I put this like this, the modulus of this has got to be less than or equal to 1, right? And since it is modulus, I can simply write the numerator and denominator separately. I can say that this is going to be the modulus of A dot B divided by the magnitudes of A times the magnitude of B. I have dropped the modulus here because magnitudes are any day positive, and this must be less than or equal to 1. Okay, and what does that tell us? It says that the modulus of the dot product has got to be less than or equal to the product of their individual magnitudes, right? So another very beautiful result that's coming through. It says take the dot product. Remember, the dot product can be negative, but what we are saying here in this inequality is pick the modulus of the dot product, and that will always be less than or equal to the product of the individual individual vectors magnitude, right? And this is termed as Schwarz inequality. One of the important results. It can be probably used later as well, but I think it's a very simple idea from dot products. Just directly using dot products and unit vectors and the value of cos theta, we can easily derive this fact. And there's one more simple fact that we're going to talk about just from this simple formula. Now, what does this say? If we really want to find the actual angle, what it says is cos theta is given by A dot B divided by the products of their magnitudes. Now this is again another very easy technique in order to find the angle between two vectors. We know how to compute the dot product by using the component formula, and magnitudes are quite simple, and when we divide this we see that we get cos theta. We just take cos inverse and then we can easily get the theta as well, right? So this session has been entirely dedicated to understanding dot products and many features of dot products, right? So let me quickly summarize this entire session. We started this session by talking about the symmetric nature of dot product, and then we came up with an interesting formula called the component formula for dot products, and then we extended this formula to n dimensions, which is here, and we talked about the angle between and specific interesting angles, like saying when it is 90 degree that the dot product goes to 0, and when the angle is 0, right, then we are also able to find the square of the magnitude from the dot product. So that's one more interesting feature that we looked at. Okay, after that we derived this fact algebraically, and we said that if the angle is really 90, dot product does go to 0. And then came another beautiful insight talking about we can look at a vector and find whether its angle is kind of less than 90 or more than 90 with respect to another vector just by looking at the idea of dot products being greater than 0 or less than 0 or equal to 0, right? So which half plane and what's the angle can be easily found out using dot products. Okay, then looking at this diagram of cos theta, there's one more important fact that we are looking at. So here a few examples that we did with respect to the previous find, and we found that the dot product of two unit vectors can't go, it will always lie between -1 and 1, because we know that cos theta is between -1 and 1, right? Now we applied this to any two general vectors and we came up with what is called as the Schwarz inequality. And the last point is that we can even get the angle. If we really want to measure the angle, we can use this formula, take the cos inverse, and we will be able to get the angle between two vectors, right? So dot product is an extremely important concept, and it has got a lot of features, and I would request that each one of us absorb these very important features of the dot product. So with this, we will try to bring this session to a close. So let's end this session with a prayer. Om Shanti Shanti Shanti.